So our last talk is from Zhengxiong. So Zhengxiong is a assistant professor actually in the CS department at CU Denver. So his research primarily is focused on the IoT and also mobile security. And then today he's gonna to actually talk about something very exciting. So why you should not play with your phone when you're on a call, video call. So yeah, Zhengxiong, please.
Thank you for the kind introduction. And I know everyone here a little bit hungry, so I will try to finish earlier. Today, I will bring our recent work about the PrintListener, uncovering the vulnerability of the fingerprint authentication that specifically by the finger friction sound. So a little about the threat model. Currently, we know there are many like video or audio calls, such apps like Skype, WeChat, Google Meet. We use mainly every day. They are kind of like instant video call or online meeting, live stream, and other firmware. They all that can have such accessibilities. And during this video or audio calls, the users may unconsciously like swiping your fingers on the screen. Maybe just some unconscious behavior. And such like searching for other apps or scrolling down for the information. This kind of finger slipping sound will transmit to other parties by this social communication software as well as firmware with recording permission. So here, we try to explore such possibility of attack that remotely infer the victim's fingerprint information based on such fingerprint friction sound during this unconsciously touch. Currently, already have some study have shown the uniqueness of the finger swiping friction sound that influenced by an individual's fingerprint biometric characteristics. So our work is based on exploring this kind of utilizing these explorations with a finger swiping friction sound to infer the fingerprint morphological features. The production of this roughness involves three essential factors related about our biometrics. First is called friction, that is elastic deformation between the fingertips and the screen. It's highly determined by our gene. Dynamics, the vibration and the wave propagate between the finger and the screen. So it's related about our characteristic related fingers and the screen. Last one, acoustics. The audio roughness sound radiate from our finger or to the surface of the phone that will propagate through the air or the medium, soft medium. We have such intuition based on this exploration that the range of fingerprint reduce the content area between the finger pad and the phone screen, resulting in the variations in this radiation about sound, solid vibration, and even the wave propagation modes. This is reflected in the characteristic of the friction sound wave. So therefore, our idea is proposed. We try to design and build a new side channel attack on our fingerprint called PrintListener, which leverages the user swiping action on the screen to extract our finger patterns and synthesize a strong master print sequential based on these features to conduct directional attack on our user's fingerprint. And especially, we aim to two aims specifically technology. First is predict the fingerprint pattern. Second is synthesize a stronger fingerprint minutia attack template. Our work has several advantages. First is stealthy. Compared to previous work on to steal or infer your fingerprint, our work is carried out by leveraging the mainstream social software with video or audio calls, do not necessarily other supplementary hardware. Second, pervasively, we don't need the large data training on specific person. You can use the master print sequential attack. It is compared to the large training, it will be quite lightweighted computation. Third one, no adversary proxying or accessibility. The attack don't need to obtain the finger pattern information through observation or approximately to the device used by the user. You can just infer such information through the line remotely. Last one, no additional user action. The attacker do not require any additional actions from the user. You don't need to ask a user to rubber on your screen several times. You don't need other user coordination. You just utilize the user unconsciously behavior. However, to achieve this goal, there are mainly three technology challenges before we can do that. First is usually the sound intensity of the finger friction sound from the user is extremely weak and also happen in a very short time window, usually range from 0.2 to 0.8 seconds. So we need exclude the noise and also extract the useful information within such a short time. Second, it's about the frequency sound characteristics. Usually, different users will have different behavior, different swiping. So how can we protect against the influence by the user physiological and the behavior features and to help us inform a robust attack? That will be a little difficult. The last challenge is about the fingerprint features. So after we can predict, infer the prime patterns, or say the level 1 patterns of the fingerprint, the potential search space for the secondary features that corresponding to the first level pattern is still vast. As you can see in this image, you can see there are many tiny features about the ridge ending and also bifurcations. Those are searching on those kind of detailed features still need a lot of computation resources and the last. To solve this problem, we propose our system. It mainly have 3 modules: data processing, fingerprint pattern mapping, and the last one is pattern master print synthesis. Data processing is mainly served for the signal analysis against the background noise interference and extract the useful information in some dynamic speech. Second module will improve the wide depth combination module to extract interpreting audios and deep representing. Last one, after we got the level 1 prediction, we got this level 1 prediction, we try to synthesize some new fingerprint. So we will use that module to synthesize some minutiae attack template. For the first module, data processing, we find usually during our finger swiping, the background noise is less than 4 kilohertz. So here we use FRI filter with a passband to eliminate such low frequency noise and also at the same time try to maintain the fingerprint information. Second, after that, we still found the signal intensity about the frequency sound is weak. So we try to enhance the target signals by degrade about the addition noise without introducing other distortion. So here, we're using a short-time amplitude and a physical spectrum noise composition technology. Next, about the frequency segmentation. So here, to actively extract the very specific frequency sound segment from the radio and try to exclude the redundant information about the frequency segment. We design a frequency and invent localization algorithm based on the frequency spectrum of the audios. We analyze this kind of signals across the entire frequency range, and then we try to localize such sound event. And with this localization, after we localize this event, we extend the original audio to stimulate a different variation of the swiping pressure or speed. And we use the technology of the time stretching and the pitch shifting to generate a range of similar but different waveform to mimic such conditions. And also, waveform resampling is also applied to extend the frequency segment and optimize the original dataset. So by now, we're using our technology to solve the first two challenges. And then, in the next module, we're using we analyze the interpreted audio features with these 6 frequency features and 3 captural domain features, try to interpret our audios, and using this kind of feature extraction to feed our classification model to predict the classic 1 feature patterns. And here, for the classification, we fine-tune a pre-trained VGG-based model to learn high-dimension features. So by now, we have finished the first aim. We have, using this VGG model, the multiple classification to get the prediction about the patterns of your fingerprint. Then the last step is try to generate more detailed about their fingerprint to spoof the user identification models. So here, after predict the fingerprint patterns, we use the random restart hill climbing algorithm to synthesize the second level of feature. It means the position and the direction of the minutiae of the fingerprint that responds to the first level. To improve the efficiency, we first will find the area about the high possibility of the fingerprint minutiae collision in the fingerprint image. And throughout the iterative process, the best performing detail template serves as the stone state. We will keep this stoned information and then as the final output. In this image, there are 2 fingerprints illustrated. On the left side, that's our synthesized one. And on the right, that's the genuine fingerprint. For evaluation, we totally include 65 subjects and collect this kind of data using 3 different smartphones and in 3 different very common working environments. And for the comparison, we import 2 very famous dataset, fingerprint dataset as the baseline. One is partial one, and another is complete one. We also include several metrics to achieve this goal: the average position, average record, weighted average position, and weighted attack success rate. We first combine these our classification with different classifier and to test their performance. And we found the VGG based with KNN based together outperform the other networks. Second, sample rate, that is most important here because we try to infer some information through the social network. So the sample rate, I guess that's the most practical inference here. We test with different sample rate, and we find the recall in classifying the fingerprint pattern, which means try to predict the level 1 will gradually decrease as the sample rate decreased. And that also worth to know that classifying accuracy of the sound at 41.1 kilohertz sample rate does not exhibit a significant distinction compared to the 32 kilohertz. The 32 kilohertz is commonly the used rate in the most radio and audio social network software. And due to the size of the certain smart devices, like mobile devices or IoT devices, many sensors may not use the complete fingerprint, mainly just use a part of your fingerprint for authentication. So here we test with complete fingerprint and partial fingerprint. And the result showing here is partial fingerprint is more vulnerable, more suffered to our attack. So here we suggest the fingerprint with the smart sensor usually may need improved more from the view of security. Lastly is about the security setting. We test with different settings, and we find the ASR decreased at low FAR values, while more test subjects are successfully attacked at high FAR value settings. For baseline compression, we test among our collected data set and also the public baseline data set, all exhibit some high attack rate. So to sum up, defense, there are two types of category can potentially defend such attack. First is correct user behavior. During this video or audio call, our suggestion try to avoid such unintentional swiping. I know it's hard, but to protect your sensitivity information, you can try to prevent such swiping as much as possible. The other category is during using this kind of audio or video social or communication app, one is lower the audio sampling rate. You can set it in the system setting. Or you can destroy the fingerprint friction sound features using some audio post-processing technology to affect our signal extraction. Last is implement some pop-up reminder. If the app detects your such unintentional behavior, pop up some reminder to the user this kind of potentially cause some information leakage. Also, we do some feasibility test. We using our devices to test on the 3 very commercial app. We found this kind of app from technology can support the enough sample rate to achieve this attack. And similarly, we test with different screen protector, temper or grosser. Maybe the grosser here in the right image showing is not have very, very weak signal intensity, but however, with a long usage, the roughness about the grosser filter will increase and also will cause the information leakage. Okay, so that's all about this work. We uncover a new side channel and hope this work can remind you during your daily life, can help you protect your information. Thank you. I'm happy to answer a question.
So probably one very quick question. Anyone? So I can ask one. So if we use a headphone, are we still vulnerable to this attack? If we use the headphone, so.
Oh, you mean the headphone?
Yeah. Yeah, I guess earphone. Yeah.
Earphone. Maybe some unconscious behavior, you will like touch or swiping the earphone. So that may also cause this kind of problem. Also have such vulnerabilities.
Yeah, but then for the swiping, those kind of things, I'm fine.
Okay.
Okay.
Yeah.
Okay. Okay. So we're actually a little bit out of time. So yeah, I guess let's thank Zhengxiong again.